Okay, so hello also everyone from my side. My name is Olympia Axelou, and I am very excited to talk to you today about our in-house tool called PROTON. It is a physics-based electromigration assessment tool for modern VLSI power grids. We will discuss a bit its core principles, the innovative methodologies that includes inside, and how we envision adapting it for 2.5 3D chiplet-based designs. First, let us explain what actually electromigration is. As the current flows in a wire, and we are talking about lots of current, the momentum of the electrons drives metal atoms from the cathode towards the anode in the direction of electron flow. Because of this, the cathode gets depleted of metal atoms and tensile stress gets built up, thus voids are created there, while migrating atoms get accumulated at the anode terminal of the wire and compressive stress is created there. Now, the derivative problem is that the resulting concentration gradient that exists due to the stress, the electromigration stress, when it reaches a critical level, it can lead to HELOX and denser material, as we see here in the anode, as well as the creation of voids and consequently to open circuits. And this is the most important part. The phenomenon of electromigration actually intensifies due to the continuous downscaling of the integrated circuits and the simultaneous increase in currents that flow in the interconnects of the lines. It is considered a major concern for nanometer scaled integrated circuits, especially in modern technology nodes in which process variation actually affects the shape. Now, because of its importance on the chip's lifetime, electromigration reliability analysis has already been included in integrated circuit design flow, although the methods used are too conservative for the modern power grid networks and are based on heuristic models. In particular, there are various industrial tools that perform electromigration analysis, such as Voltus by Cadence, RedHawk by ANSYS, which is integrated into IC compiler, and also COMSOL Multiphysics, which is a FEM simulation software package for various physics and engineering applications. Now, the problem is that all these tools although they offer a bundle of analysis, none of them is actually explicitly for electromigration and how it involves in modern power grids and designs. Also, they make use of Black's equations, which is a mathematical model that calculates the mean time to failure of a semiconductor circuit due to electromigration. And it is an empirical method. It is actually heuristic, and now it is often inaccurate for modern integrated circuits. And last but certainly not least, all these tools are closed source software, and the user needs to pay in order to get access to them. However, the EDA community has shifted its focus to open source and embracing initiatives such as open source software strategy by European Commission and along with other large-scale EDA projects like Open Road in the US. PROTON actually aligns perfectly with this action, which can enable smaller design teams and individuals to benefit from cutting-edge electromigration analysis, fostering this way innovation and collaboration within the EDA community. It's actually something very needed. Now, having said all that, we present PROTON, an electromigration analysis tool for power grid lines that is designed to be fast and efficient. It actually leverages parallelization and optimized algorithms to handle large-scale power grids. It is an open source and cross-platform EDA tool with intuitive graphical user interface and an easy command line version, which makes it very versatile for any power grid design flow. Now, let's proceed to what is actually in the core of the tool. For accurate electromigration stress analysis, in the core of the tool, we employ the physics-based equation proposed by Korhonen. It is a partial differential equation that models the diffusion of electromigration stress inside a line or an interconnect. And accompanied by the suitable boundary conditions, then we create, and using the FDM discretization, we result to this system here, this ODE system here of size n, which is actually the discretization points. Now, PROTON offers two key functionalities. First, it can perform line analysis, which is very fast, a semi-analytical method, in order to calculate directly electromigration stress on power grid lines at a specific time. It keeps the time continuous and takes advantage of the specific form of matrix A, the diagonal matrix A, and performs discrete cosine transform type 2, which reduces the complexity of the calculation from n squared to n log n. Now, on top of that, this method is completely parallelizable for the different lines in a power grid. So this enables the use of multiple threads for complete power grid EM analysis. And now, if we want to specifically calculate and see the transient response of a specific point, we have the point analysis, in which Proton calculates the specific transient analysis of a specific point. And here, in order to do that efficiently, beginning from this state space model that our tool has, we employ an EKS, extended Krylov subspace model order reduction method, in order to lower the complexity of the system by projecting it to a much lower dimension subspace. For this purpose, it leverages the fact that the stress is proved to be more pronounced in the vias and endpoints. So our tool focuses on this point, but it is not limited only to them. So both core methods have low complexity, and thus they are very efficient. And because of the nature of the methodologies, they also are robust and provide accurate results with minimal error. So the Proton core technology was implemented in C++, providing the computational power needed to efficiently perform complex matrix manipulation tasks. For this purpose, Proton, of course, utilizes Eigen, which is a powerful C++ library for linear algebra operations, and which actually provides a specific module called sparse that allows efficient storage and manipulation of very large sparse data structures. And this allows us to handle large-scale benchmarks and accurately and efficiently while having low memory footprint. We further enhanced our tools by linking Eigen to Intel MKL, a highly optimized numerical library that is designed to take advantage of the specific Intel processor's advanced features, such as vectorization, parallelism, and instruction set optimizations. This means that Eigen, along with Intel MKL, can achieve significant speedups in sparse matrix operations. Also, these two libraries are accompanied by C++ library collection called Boost, in order to further enhance the functionality and the performance of the application. Now, for the line analysis and the efficient formation of the analytical solution, Proton leverages the state-of-the-art FFTW library to perform the DCT type 2 discrete transformation required for the analysis. The library is actually widely recognized as one of the fastest and most optimized solutions for performing fast Fourier transfer, ensuring that Proton can perform line analysis quickly and effectively. On top of that, it also uses OpenMP in order to leverage the parallelizability of the line analysis algorithm, which enables us to perform fast, complete power grid analysis. Now, as for the Bayes transient analysis, the internal steps utilize Paradiso solver, a highly optimized and widely used direct solver for large-scale sparse linear systems. This solver ensures a robust performance, which results to reliable solutions and efficient memory usage, something very important for the EDA tools. So as a result, the methods that are incorporated into Proton, along with the libraries used for their implementation, make Proton an excellent choice for efficient and trustworthy EM analysis that is applicable to all power grid sizes while offering robust analysis. Now, having discussed the underlying internal components that form the core of Proton, we will now shift our focus to a broader perspective in order to analyze the proposed tool on a more complete manner, let's say. So, to do that, this is the flowchart of Proton. First, we have the parsing stage, where Proton receives the power grid design in SPICE format. Then, once the power grid design has been received, Proton communicates with an external circuit simulator in order to obtain the currents flowing through its line. It can be any industry standard or open source SPICE simulator, which makes Proton actually easily integrated into any physical design of states. Then it parses the SPICE file and extracts all the lines of different nets and layers. And then it generates some general NDM-related statistics on the power grid, as well as the complete set of the extracted lines. After selecting the line and the desired configuration, for example, technology, temperature, the width of the line, etc., it discretizes the line with using finite difference method. Then, depending on the analysis, as explained above, the user can choose between the two previously discussed analyses that are integrated inside Proton. And finally, of course, the users can plot and extract the results. And as we said, the primary goal of Proton is to be compatible with typical industrial design flows. This is actually guaranteed by the use of the widely accepted SPICE format for power grid design. For the parasitics. Also, we are always in sync with the present industrial design methodologies and commercial EDA tools as we integrate in the flow of our tool external circuit simulators like HSPICE by Synopsys and Spectrum by Cadence. This makes it very easily integrated into any power grid design flow. And finally, as can be seen, our tool has been implemented in such a way that it's offered a great level of automation that makes it very friendly, user-friendly and intuitive. Now, in this context, the user interface of Proton is designed in a minimalistic way using the PyQt5 library of Python. By diving a bit into the user interface, we have the following components. First, at the bottom left, we see the power grid panel with all the parsed lines of the power grid hierarchically displayed of its metal layer. Then we have the configuration panel where we set the analysis options like the technology of the power grid line, the temperature, the width. We also have there the discretization of the line. Then after selecting a line, its geometric plot is automatically displayed in the top of the screen. So that the user can fully understand its geometry and all the segments that compose it. And after an analysis is performed, the corresponding plot is displayed in the middle of the screen. And finally, at the bottom, we have a space for message log and statistics of the analyzed power grid. Now, as for the toolbar, of course, we have the file menu with new, save, open, etc. things. Then we have the simulate menu where the user can select the desired simulation and the simulation parameters. Then the plot menu in order to display previously run simulations and the export menu for various reports and statistics. Overall, the user interface is rather intuitive and simple, or at least it was designed to be that, which further enhances the user experience by effectively encapsulating all the state-of-the-art methodologies and libraries in a simple and user-friendly way. Now, in addition to the aforementioned user interface, Proton also provides a command line version for a more automated run of electromigration analysis. It follows the same flow as mentioned in the previous slides, and which are organized and split into simple commands. Also, Proton offers the option to source TCL files, TCL scripts, that can be used to fully automate the electromigration analysis process so that it can be seamlessly integrated into any power grid design flow. Now, I encourage you to actually check out our tool and try it. You can find it on GitHub, the complete installation guides and detailed documentation. And actually, whether you are an academic researcher or a design engineer, we think that Proton can help you very much gain insight on the physics-based behavior of electromigration phenomena. And now, in order to conclude my presentation, let us take a step forward and think about chiplet-based designs. Now, chiplets bring unique challenges to electromigration analysis. The increased interconnect density and complexity can significantly impact reliability. And when introducing heterogeneous integration, we are faced with non-uniform stress profiles that are tough to predict. These issues are amplified for vertical interconnects like TSVs, microbumps that create stress hotspot. To adapt Proton for this evolving landscape, as we can say, the primary step is actually to extend the power grid line analysis to account for vertical interconnects in order to seamlessly build on the solid foundation 2D analysis. This way, we aim for a smooth transition between the 2D analysis that we are now into the 2.5 3D power grid analysis. Finally, and this is something that I believe very much, collaboration between the industry is actually the key here. Validating on real chiplet benchmarks will be crucial to tuning the simulation methodologies and gaining insights into practical deployment. And as the industry increasingly shifts towards 2.5 and 3D design flows, Proton's flexibility will make it an invaluable tool, we hope, in ensuring reliable chiplet-based systems. And of course, the ultimate goal here is to continue democratizing electromigration analysis and keeping everything as open source as we can, while staying ahead of emerging design challenges and thus bridging the gap between the traditional VLSI and the future of 3D integration. So, yes, that's it from me.